All right, recording is rolling. It's Tuesday, January 9. We're gonna make these lab graphs from this Pendulum lab from yesterday. Right? So some of you guys might already have these graphs, or some of them. As I was walking around yesterday, it looked like some students were getting the graphs right, and some students were getting them wrong, and some students were getting like half right. So we'll put them together, and then you guys can check your work. Okay. And then I gave you guys thumbnail notes for the new set of posters. So we'll do those today. Demos, yeah, my first period class, I was trying to shuffle back and forth between these two. I think I'll save some video demos for tomorrow. It's going to back up some concepts you guys are going to see today. Right? Oh, tomorrow we do have this weird schedule. So let me switch my screen just to, no, hold on. Let me pause this. Looks like this is disconnected. Okay, hold on. Pause. All right, we're back here. All right, and so here's what's going on tomorrow. All right, tomorrow, go to your homeroom class first. You'll be there till 10:25, and then you'll go to all your other classes for half an hour each. Your lunch is going to be with your fourth period class. So guys, your fourth period class, check what lunch you have so that you know whether to go to lunch first or to your class first. All right, so that'll be tomorrow. All right. Okay. So okay, we're going to get volunteers in a few minutes to get some data so we can put these graphs together. Okay, this is the graphs this time, you guys. Right. Right for that, let me recap what you guys did. Right, so you guys were making pendulums yesterday. Right? Put different lab weights on string, let's swing back and forth. And we're trying to figure out what is the relationship among these variables. Right? The mass of the bob, the starting angle from the vertical, the length of the pendulum, and how much time it takes to swing back and forth. Right, would be one time period. Right. The variable that I don't have listed here is gravity field of the planet, which also does matter, but can really change that. Right? So right, there's a control in the background. Right. Right. And since there's 4 variables, you guys had to do 3 different experiments. Right? So I had you guys relate everything to time period, treat each of these other 3 variables as an independent one at a time, and control for the other 2. Right, so it's 3 different experiments. Now we're going to put this all together and come up with a master equation so that we can predict for any pendulum how much time does it take to oscillate back and forth. Right? So let's set some axes. I think you've got some good data in front of you, so I'm about to get some volunteers. So we're going to make these graphs. Right? So the first graph, let's do time period versus mass. Right? This is, of course, that constant angle and length. Okay? So I'll go time period in seconds, and we'll go mass in, well, either grams or kilograms, but I'll see, what do you guys come up with? Okay, so who wants to share their data for that one? Okay. All right, Tucker, what was your largest mass?
This is for time versus mass.
Yeah. Yeah, what was the largest mass you used?
The largest mass we used, 1,000 grams.
1,000 grams. All right, so let's go mass in grams. Scale this up to 1,000. So 200, 400, 600, 800, 1,000. Right? So start at 0, 200, 400, 600, 800, 1,000. Okay. Again, you might have this graph or not, and if you do, you can check your work and see if you did this right. Okay. Right, so for that 1,000 gram mass, how much time did that take to swing back and forth?
1.03.
1.03 seconds. So let's go time in seconds. Call this 0, 0.5, 1.0, 1.03. It's just above 1. It's probably right about there. I'm gonna go. Okay. So bam, got a point on the board. Okay, so what's another coordinate?
1.37.
1.37 seconds. All right.
Yeah,
and
that was the largest number we got.
What was the mass for that one?
20 grams.
20 grams. All right. 20 grams, 1.37 seconds is probably right about there-ish. Bam. All right. What else you got?
1.19.
1.19 seconds. Right. And what was the mass for that one?
50.
50 grams. All right, so probably right about there. All right, what else you got?
1.06.
1.06 seconds. And how much mass?
100 grams.
100 grams. All right, right there. All right, what else?
1.14.
1.14 seconds. How much time or how much mass?
500 grams.
500 grams.
And for 1,000, it was 1.
All right. All right, there you go. All right. So it looks like it slopes down a little bit. All right. But overall, it's pretty flat line. I think overall, like the overall trend is probably pretty flat like that. I think, right? Which would indicate no relationship between those two variables. Okay. So you can start off with a tiny mass and then make the mass like crazy bigger proportionally, but the time period doesn't really change, not a whole lot. Right? Now it does look like it actually slips down a little bit, right? But I think that actually does make sense too. And the reason has to do with the geometry of these masses. Like if you have a little tiny mass versus get bigger and bigger masses. Okay? If you're connecting them all, like if you're hooking them at the end of the string, okay? Well, what is the effective length of each one of these pendulums?
Rotational inertia.
All right. Well, you're going from the point that's swinging about to the center mass of the mass itself, right? Okay. Which, if you're working with a little tiny mass, is probably like right about here. But the big mass is like way down here, which actually adds some length to it, right? Okay. So even though I said constant angle and length, that's not exactly true, right? For the larger masses, the length actually does get a little bit longer, which you might remember from yesterday, probably like slowed it down a little bit, right? Which would actually be a good reason that graph would slow down a little bit. But if you control it with that, it's pretty much no relationship right there. There we go. So let's do next one. Okay, time period versus angle. This is at constant mass and length. Right, so time period in seconds versus angle in degrees. Okay. Oh, I remember what else I meant to say for this first one, right? Time period versus mass. Okay. You might have hypothesized this yesterday, just because we did do something really similar to this last semester. Last semester, I had you guys set up a pendulum just so you could calculate and then measure what was the speed at the bottom of the pendulum. And the way you calculate it was through conservation of energy. So it was going from mgh to 1/2 mv squared, and the mass actually canceled out, which means that the mass has nothing to do with the kinematic motion of the pendulum, which is what those shows do. Okay. So now we're going to change the angle. Right, so he's got some good data for this one, for the angle. All right, how about let's get another volunteer. How about Adam? Right, what different angles did you? What was your largest angle?
Our largest angle was 75 degrees.
75 degrees. All right. So let's go 10, 20, 30, 40, 50, 60, 70, 80. Okay. So 0, 20, 40, 60, 80 degrees. Right? Okay. And for 75 degrees, how much time did that take to swing back and forth?
So on 75, it took 1.56 seconds.
1.56 seconds.
Yeah, you might want to make like 2 at the top.
Yeah, that's probably a good idea. Down here. Yes, yeah, right. So 0, 1, 2. Yeah, like that. I think that worked, right?
Yep.
Okay. All right, so it's 75 degrees, and sorry, how many seconds?
1.56.
1.56. 1.56. Right about there. Right, there we go. All right, what's another coordinate?
Another coordinate, we have, say, 30 degrees and 1.38 seconds.
30 degrees,
yep.
1.38 seconds. It's right about there. Bam. All right, what else?
we have 15 degrees and 1.47 seconds.
15 degrees, 1.47 seconds. Bam, right there.
We have 45 degrees and 1.52 seconds.
45 degrees, 1.52 seconds.
Yep. And lastly, we have 60 degrees and 1.53 seconds.
60 degrees, 1.53 seconds. All right, got that. Ooh, so what do you guys think for that one? What relationship? No relationship. Yeah, that's again a pretty flat line. Okay. So it doesn't really matter, what angle it's swinging from. It takes the same time to swing back and forth, okay? Which maybe hypothesized or maybe not. I think the first person to either notice this or write this down was actually Galileo, who's watching a pendulum swing from a ceiling. And of course, he didn't have stopwatches back in the 1500s, but he was using his pulse, right, as a rudimentary stopwatch. And he noticed that, yeah, whether it was swinging from like a 5-degree angle or a 20-degree angle, it didn't matter. It's the same time period to swing back and forth. Okay, so all right, the first two variables we're testing, the mass and the starting angle, have nothing to do with how much time it takes to swing back and forth, right? So mass and angle are not going to be part of the equation that governs the motion of the pendulum, at least for time period. Okay. Right, so we've got one more variable, which is the length of the pendulum. I'm going to set 2 graphs here too. We're going to do 2 graphs related to this, these side by side. Let's go time period versus length. Okay, this is at constant mass and angle. Okay, so you got time period versus length. Okay. Let's grapple. Save later. Okay. Okay, so he's got some good data for time period and length. Period length. How about Aaron? What was your longest length? 36 centimeters. Let's go centimeters. Okay, scale it up. 36, right? Let's go 10, 20, 30, 40. So 0, 10, 20, 30, 40. Right? Okay. So 36 centimeters. How much time did that take to swing back and forth? So 1.4 seconds? 1.04? All right. Let's go. 0.5, 1.0. Okay, so 1.04 seconds. This is 36 centimeters, 1.04 seconds. Okay. Okay, let's know that coordinate. 33 centimeters, 1.03 seconds. Ooh, okay, sorry about that. Okay, plus
28 centimeters.
Okay, 28 centimeters, 0.97. Okay, sorry about that.
How many centimeters?
28.
28, thank you.
Yeah, 28 centimeters.
25 at 1.06.
1.06 seconds was 25 centimeters. Okay.
And then 25 is
20.5 and 0.81 seconds, 0.81 seconds. Right there. All right, is that it? This one. All right. All right, yeah. Now, what I'm going to do is this point right here, I'm going to call this guy an outlier. Outlier. Right. Sometimes I know do experiments and maybe I don't do something quite right, and then look at the data points and say, oh, didn't quite land on the curve, right? But all these other 4, ooh, looks like they're kind of trending up and to the right, sort of, right? Right, now, what kind of relationship is that? No, if I put this graph together, I had more class time, I might go back and say, hey, let's test out like 10 centimeters or maybe even 5 centimeters and see what happens as we approach like a shorter and shorter pendulum. Okay? But I think we can get it just from this, right? Because it's like, okay, well, that might possibly represent a linear relationship, right? But if that was true, then would it extrapolate backwards to a huge y-intercept, about half a second or so, right? What that would mean is that if you had a really short pendulum that should definitively be about like half a second swing back and forth. I don't know if that quite makes logical sense, which might hint that this might not actually be a linear relationship. This is something that we've run into in the past, like a bunch of times. Because if that's not linear, what relationship do you think that is?
Exponential.
Or about a like a square root. Yeah, it'd be like a sideways parabola.
Oh.
Yeah, sideways parabola is square root. Right? Okay. Here. So side thought here, if you were thinking exponential is a different classic curve. So we're dealing with square roots. It looks like here I'm going to guess that time period is proportional to the square root of L, which is the same thing as L to the 1/2 power, which is just invert of L is proportional to T squared. You can think of it that way, right? This is what I'm thinking this is looking like. Okay. Now, exponential is a different classic curve. Exponential is like if you have, well, instead of x squared, it'd be like 2 to the x, right? Which is gets really big really fast. To the x, like exponential, that's like interest rates or like inflation or things like that, right? But yeah, not something you really see in this class, right? So like parabolas and roots we're usually doing, right? So if I'm going to suspect that time period is proportional to the square root of L, right? Something like that, right? Or I could say time period squared is proportional to L. Now, if I suspect that's true, then if I make either one of these graphs, then these points should line up on a straight line, right? And the advantage, well, there would be two advantages of that. One is that it would confirm this was in fact a square root relationship rather than like a cube root or something else like that. The other advantage of a straight line is that it's really easy to make an equation because you just do rise or run, get the slope really fast, and make an equation, and we can compare that to a textbook equation. Okay, so let's do that. I'm gonna square all the time. Oh, oops, I forgot to label the unit here. Oops, big oops. This is in seconds, right? Oops, seconds, right? Because we got to know what we're looking at, right? Time period in seconds. Okay, so I'm gonna use this bottom one and model this. So what if I do time period squared and squared seconds versus say like the length, right? Also, I'm going to switch the length to meters just to have it in base SI units, but otherwise you could just copy paste that axis. Okay? So that's going to do that. So I'll call this 0, 0.10, 0.20, 0.30, 0.40. That's meters now. Okay. And time period squared. Well, the biggest time periods were just over a second. If you square that, it's again going to be a little over a second squared. So probably scale it about the same too, right? Okay. Call it 0, 1.0 square second, or whoops. Why is it doing that? 0.5 square seconds, 1.0 square seconds. Like 1.5. All right. So I did write down one of these coordinates so I can square that. So what 1.04 seconds and square that, that's like 1.08 square seconds. So 36 centimeters, 1.08 square seconds, 1.08. That's probably right about, actually, it's close to there. So 0.36 meters, 1.08 square seconds. Okay, so there's the point on the board. Okay. This other one they didn't write down. So, Aaron, you got a calculator in front of you? Calculator? Okay. All right. So we had to go ahead and square the times. Let's run along. So what was the second longest pendulum? It was 30 something centimeters. Oh, 33 centimeters. And if you square the time, what does that come out to? 1.06 something. Okay, so that's just a shade less than that one. So we're right about there. Okay. Then how long was this one? 20 what centimeters? 28 centimeters. Right. So 28 centimeters. And if you square the time, what do you get? 0.94. 0.94. 5, 6, 7, 8, 9, 94. It's right about. It's right about there. Okay. And then, okay, I'm going to skip over this guy. Okay. Your shortest pendulum was that 20.5 centimeters, I think you said. Okay. And if you square the time, what does that come out to? 0.656 square seconds. Okay. All right. All right, so okay, yeah, that looks closer to a linear relationship, right? Like we do line of best fit, be pretty close to pretty close. Yeah, that looks pretty linear at that point. Okay, so we're gonna call that linear, right? And one of the coordinates, okay, it looks like it passes pretty close to the origin, so I'll call the origin a 0, 0 coordinate, right? And I've got this one labeled, right? And it looks like that line best fit goes pretty close to that point too, so I'll say it does, so that I can get a slope really quickly. Just this rise over this run. Okay. Let's see what is that? What is 1.08 square seconds divided by 0.36 meters? That's rise over run. Okay. That tells me the slope of, oh, whoa, I didn't expect that. Right, 3 exactly. Look at that. 3 integer, crazy integers. So it'd be 3, that'd be square seconds per meter. Square seconds per meter. Okay. Which means we can make an equation now. Right. So y equals mx. Right. So y is like t squared. So I'll say t squared. I'll say equals this equation. Okay. So slope is 3 square seconds per meter. Right. That's times the length. Or you could square root both sides and get a little bit different perspective for that equation, right? But now you can have a pendulum of any length, and as long as you're on Earth, you can take that length, multiply by 3, right? And then take the square root of the whole thing, and that will tell you how many seconds it takes to swing back and forth, right? I'm gonna say put the length in meters, right? Okay. So what is the textbook answer to this whole thing? The textbook answer says time period is equal to 2 pi times the square root of L over G. Okay. So we do some more stuff with that. Okay. How about I take the textbook answer and I square both sides to make it look more like what I had right there. So I've got T squared now equals, right? So if I square all this stuff, I've got 2 pi quantity squared. Okay. Now the G I'm going to bring out here. And then square root of L squared is just L. So, okay, so now, right, this and this are the same thing. But now what I just wrote looks a lot more like this boxed in answer from you guys' lab, right? So you can do is see how close you guys got, right? So what's this whole 2 pi quantity squared divided by G? Okay, now your guys' data says it should be pretty close to 3 square second per meter. Let's run the numbers. So 2 pi quantity squared divided by, I'm going to use about 9.8 meter per second squared for G. Okay. That comes out to, 4. Right? Okay. That's pretty close. 3, 4, that's pretty close. Right? So go like that. So here's what the textbook says, and you guys got pretty close to that. Right, so pretty good. All right, you guys go there? All right, so okay, so now you guys have have a way to describe a motion of any pendulum. Okay. As long as you're on Earth, you know how much time it's going to take to swing back and forth. Right. All right. So that lab, hold on to it for a few minutes. I'll have you guys turn that to the grade tray right before you leave class, and then I will put those points in the grade book. Right. So let's go through the next set of posters. They're hanging around my room. I just printed you guys the thumbnail version. Right. Now, a lot of these video demos I'm going to save for tomorrow. Right. So I'll be shuffling back and forth, and then yeah, tomorrow we'll have these short classes anyway, so it'll be a good demo day tomorrow. Okay. All right. So first poster, you guys can follow along with the thumbnails if you want, or you guys can take notes if you want. Okay. And a lot of these posters today I'll back up with some video demos tomorrow. Okay. So classic pendulum. Oh, here you go. Here's your guys' lab yesterday, and the answer pretty much you guys got. Right. Okay, so what kind of question could you get from a textbook for this? Well, you could be asked. Here, I see 3 variables here, right? Time, length, and gravity field. Right. You could be given any 2 of those and asked to solve for the third. For example, if you're an astronaut exploring planets and you land on some planet, like, hey, what is the gravity field of this planet? Break out a pendulum. You know how long the pendulum is, you know how much time to swing back and forth. You can calculate the gravity field of the planet. That you could be asked a proportional question. So suppose you have 2 pendulums side by side, right? And one of them is like 4 times the length of the other. See, 4 times the length. Guys, what would the time period be for 4 times the length? What's the square root of 4? 2, right? So it would take twice as much time to swing back and forth. Sorry. Okay. So like that. Oh, here's the lab you guys just did. So you guys get that. Oh, here's all the graphs that are in front of you guys right now. Right, that's the 4 graphs that we just made. Right, just like that. Ooh, what if you have a non-bob pendulum? Because all the pendulums you guys did yesterday are just in general. We always have like some mass on a string, and the string is tiny, negligible mass compared to the bob, right? But what if you have like a hanger on a doorknob and it's like swinging back and forth? Well, that's not exactly that, but it's kind of similar, right? This might be the only time you guys see this, but you guys remember I is rotational inertia, right? What I do want to show you guys right now is that this does simplify to the equation that's set in front of you guys right now for just a regular classic pendulum, right, with bob. Because the classic pendulum, let's go back and find that. This looks like this, right? What is the rotational inertia of a point mass? Is that mr squared? You guys remember back from December, it's mr squared, right? So I got this m, this radius squared. Oh, and this radius is the length, so that's L. So I can call it ml squared, right? And I can substitute that right here for this I, ml squared, right? Well, this m and this m would cancel, and one of the L's would cancel. You have another L. So that's 2 pi square root L over G, which just turns back into a classic pendulum. You guys are going to see pretty soon, we'll do a lab that involves, give you guys some springs, some lab weights, and if you attach this lab weight to the spring and let it oscillate back and forth, there's some time period associated with that, right? It looks really similar to the pendulum formula, right? Instead of L over G, it's M over K, okay? Got the mass, got this bob, we got, hey, the spring constant, how stiff is the spring? Okay? If it's a really stiff spring, it's a very small time period, right? So if it's not a very stiff spring, maybe it's like, if it's a really stiff spring, maybe it's like, right? Really time period, really small time period to go back and forth. And so we'll do a lab, pretty soon on that one. Okay. Let's look at some oscillatory variables. Okay. So t time period is how much time does it take to swing back and forth, right? But the reciprocal of that is a related concept called frequency. Frequency is going to be measured in hertz, which is like 1 over seconds. 1 over seconds is hertz, cycles per second. Right? I should have put hertz somewhere on there. Okay. So actually, here I will do one demo with you guys, just to be auditory. Right, so let's listen to this file. Right, so you guys hear 1 beat per second, 1 beat per second, right? So 1 beat per second, the time period would be 1 second, right? And then if you take the reciprocal of that, that's 1 over 1 seconds. It's called 1 hertz, right? So 1 beat per second is called 1 hertz. Okay, let's speed that up a bit. Are you guys hearing 2 beats per second, right? Is that like 2 cycles per second? Do you guys think that would be called 2 hertz? 2 hertz, right? And how much time is between beats?
I don't know.
Half a second. That's what I was looking for. Half a second, right? Right. So if you do 1 over 2 hertz, that's, yeah, half a second between beats, right? Let's speed it up more. Are you guys hearing 4 beats per second? Right. Could that be called 4 hertz? 4 hertz, right? And how much time between beats? Yeah, 0.25 seconds, right? Because 1 over 4 hertz is 0.25 seconds. Right. All right. Let's do one more. Kind of hard to keep track there. Do you guys think that was probably about 8 beats per second? 8 beats per second? Could you call that a frequency of 8 hertz? Right? And how much time between beats? 1/8 of a second. Right? 1/8. Oh, right. What if I kept increasing the frequency? Do you guys think at some point your brain would lose track of the beats and it would sound more like a hum, like, and then you keep turning up, like, it sound like more like a musical note? You guys think like a musical note? Right. Actually, all musical notes have an associated frequency. I have a box of tuning forks here that we're going to use at some point. Okay. Now these are tuned weird. I think this is called scientific tuning or something weird. But so these might not exactly match instrument frequencies, right? But this one says 384 G, right? That 384 means like 384 hertz. So if you had like 384 beats per second, your brain wouldn't be able to pick up beats. It would sound like a hum. It would sound like a G note, according to this. That's like 384 hertz right there. So we'll use those for lab person here. Okay. All right. Now there's another type of frequency, a different perspective on a frequency called angular frequency, which is about to help us out making some graphs. Look at some graphs. Okay. So if you take that frequency and multiply by 2 pi, okay, great. What's that good for? It's going to help you put these graphs together. So do you guys maybe in a pre-calc class make like sine and cosine graphs like that? Right? So if you graph me like what is the horizontal location of a bob yesterday for yesterday's pendulums, I bet it would look really similar to this one, right? Or I guess either of these scenarios, right? Something oscillating back and forth. Right? And so you could describe this with a sine or a cosine curve. Usually displacement, you start with cosine so that at time zero you have some initial displacement, maybe pull it back, right, and then let it go, something like that. Right? So oscillates back and forth. Okay? So this could be a sine or a cosine. Here I've shown a cosine. Right? This A is the amplitude, so it's like how tall is this curve, like from the time axis. So this distance right here, call it amplitude. Right? There's some kind of periodic motion, so I need time as like the horizontal axis. Right? So that there's that variable right there. Right? And then like how stretch or squash is this horizontally? Right? Well, it's related to the frequency, but graphically it's easier to like sine and cosine. You guys know oscillates every like 2 pi radians is one complete cycle, right? Okay, so we're going to bring in a 2 pi f and call it angular frequency. Okay? And then once you have that constructed, it's really easy to whip off the velocity and acceleration graphs, and there's going to be a pattern that develops. Right? Question: how many guys are in calculus? How many guys are in calculus? Right? Yeah. Okay. So some guys, right? Now calculus is about rates of change, right? Rates of change, right? And there's a lot of crossover concepts in physics. Like the rate change of location is velocity. Rate change of velocity is acceleration. Right? So if you're in calculus, what is the first of all, what's the fancy term for rate of change? Starts with a D. Derivative. And what's the derivative of a sine graph? Cosine. What's the derivative of cosine? Negative sine. So start with cosine, take the derivative, rate change. Okay, so going from position of velocity. Hey, look, cosine turns to negative sine. And negative sine, derivative of that is like, oh, negative cosine. This is gonna be like a 4-part pattern. One more thing. If you take this angular frequency, notice it comes out, and it comes out again. Right? Right? Yeah, squared right there. Right? What's that rule called in calculus? It's called the what rule? Like, why is this angular frequency coming out and then come out again? It's called the what rule? Chain rule. Oh yeah. Yeah. How about this perspective? So what if you have a mouse on a string, it's bobbing up and down. This one's bobbing right and left. Okay? And you match this up to, how about a car going around a circular track at constant speed? Right? They would actually align. Like this would align, like this might be north, south, or up, down. Right? And this one like east, west, or right, left would align. Right? Because you guys remember on a unit circle, sine tells you how far high or low you are on the circle. Cosine tells you how far right or left you are. Okay, so we could align like that. Different perspective there. Linearization. Hey, we just did some linearization, right? We took this, linearized it. Actually, this was exactly the graph we just made back earlier today. Right? Time squared versus length, line of a straight line. Right? So if you follow through the variables, this is actually the slope is what it ended up being. Right? 2 pi quantity squared on g. Got what do you get, like 3 or 4 seconds squared per meter, something like that. Okay, right? Mass on a spring, bobbing up and down, really similar looking setup right there. All right, let's look at properties of waves, wave properties. Okay, so here I've got a classic transverse wave. If you take like a string or a slinky, I got a slinky over here. I think tomorrow I'll do a demo day, right? Like shake this up and down, right? Create like this classic transverse wave. How can you, what are different properties of this? Right, so amplitude, A is amplitude, right? So like, how tall is this from this node of line to the peak? Sometimes you hear something called wave height. Wave height is twice the amplitude, right? So if you double the amplitude, that's like the total wave height from this crest to this trough, something like that, right? If you have a standing wave, now not all waves are standing waves, but it can be, right? What that means is that you'll have these nodal points. So if I shake something up and down, I'll probably just do this tomorrow with you guys. Okay? In such a way that there can be these nodes. So if you walk up and touch the node, it won't actually affect the motion of the wave. Right? So you shake this up and down. Okay? Like a microwave in your microwave oven is an example of a standing wave, right? Where there will be these nodal points, right? how about these equations down here? So frequency and time period of reciprocals, we just look at that a few questions ago. Okay. Here's a really important wave equation. This says v, like velocity or speed of a wave, like how fast the wave propagating energy left to right, right? Is wavelength times frequency. Right? Here's wavelength. Oh, I forgot to mention wavelength. Oops. Right. Wavelength. You can go. Wavelength is what's the shortest section of wave that you could copy paste next to itself, and you could just repeat, make a classic wave. Right. You could count that as crest to crest, is one way to do it. You could go trough to trough. You could go this node, skip a node, and go to this node, like one full S shape. Right. It's one way to do it. Right. And that's Greek letter lambda. Right. So that could be in meters. Okay. If you take meters, multiply by hertz, which is 1/seconds, that gives you meters times 1/second, meters per second. Hey, which could describe speed. There you go. Speed is wavelength times frequency. It's how fast it's propagating energy. Okay. There's two main categories of waves. Some textbooks sometimes have other ones, but I think pretty much categorize one or the other here as transverse or longitudinal. Okay. So transverse is the one that's easy to draw. You just like whip off a sine or cosine graph or like an S shape. Like that, right? Oh, guys, how many wavelengths do you guys see in my transverse wave? How many wavelengths is that? Is that 1, 2, 3? Yeah, you guys see 3 wavelengths, right? And you can keep going on. You got like a million wavelengths. 1, 2, right? Property of a wave, transverse wave. I think I'll play you guys a video demo tomorrow. So if you think about this, and then tomorrow when you guys see a video demo, okay, is that the motion of each individual particle and the propagation of the energy are perpendicular to each other. So each individual particle might just be moving up and down, up, down, up, down, up, down, but the energy might be propagating like left to right. Hey, does this look like kind of like ocean waves? Maybe ocean waves could be, right? Or light. Light is another example of a transverse wave. Right. If you ever have polarizing filters, polarizing sunglasses, the fact that light is transverse means you can polarize it, right? And you can do something like this, right? These polarizing filters let light through in one particular direction, right? One direction light gets through, right? So if it's like horizontal here and horizontal here, great, all light gets through. But if you do horizontal, then so it's 90 degrees, make it vertical, right? Now the fact that light is transverse, it blocks all the light that way. Okay, guess that. Right? You can do those polarizing glasses if you have those. Okay? Now longitudinal wave, this is sometimes called a pressure wave. Where you have these high and low pressure points. Sound is an example of a longitudinal wave. So how you're hearing me right now, like from my voice to your ears, there's air between us. And if you can see the air molecules, they'd be something pretty much like this, right? This high pressure, low pressure, high pressure, low pressure, high pressure, low pressure, right? They'll oscillate, right? The closer these are together, that like a low frequency, high pitch, or sorry, high frequency, high pitch, right? Small wavelength, right? And the more they're spread out, that's like a low pitch. Interference. So constructive and destructive interference. So you have a couple of wave pulses headed toward each other. Right? Well, when they're crossing over each other, you can just add their amplitudes. So 2 units plus 1 unit, like 3 units tall. Okay? And actually, there's more to the story. I said after here, but maybe I should say like during. And then after would be these pulses will actually continue on through each other. So I've got a video demo to back that up too. So tomorrow when I'm playing those, look for that. Okay. If you have destructive interference, well, they could say subtract from each other. Right? So if you have 2 units plus -1 unit, gives you 1 unit. Right? 2 plus -1 is 1. Right? These will also go ahead and these pulses will continue right on through each other. You do something like that. Right? Now, if you can have these constructive and destructive interference, you can use that if you have a bunch of those to create an interference pattern, which could tell you that you're working with waves in the first place. Right? So what if you have this card down here, like a card, you punch a couple of holes and you put this in a water tank and you vibrate the water. Bzzz. So you've got a bunch of ripples going out. Right? And then something called Huygens principle, the ripples will say like, as they're going through these waterways, going through these 2 slits, you originate from here, originate from here. And now you have this periodic constructive and destructive interference. And on, say, like a back wall, you get like this interference pattern, right? Which you only get if you're working with waves. Right? So there's been a question in physics for like hundreds of years. It's like, what is fundamentally like some parts of matter, like light or electrons, right? Is that fundamentally particles or waves, right? See, particles, they have like mass and velocity and location and blah, 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 right? Waves have, well, they create interference patterns is one thing that waves and only waves will do, right? So if you have a question as to whether like light or electrons could be categorized as one or the other, right? This is an experiment that you can do. A famous experiment called double slit experiment. When we talk about quantum mechanics, this is going to come back, right? If you shine electrons through these two slits, they'll oftentimes create actually an interference pattern on the back wall. So electrons actually have more wave-like properties than particle-like properties. Right? So hold on to that idea because that's going to come back later. A lab I'm going to have you guys do probably next week, I think, is I'll have you guys set up standing waves and pipes. Right? So, oh, you guys remember that box of tuning forks I just showed you guys? Right? So if I hand you that box of tuning forks, you strike that over, let's say, a PVC pipe that I have dunked in a beaker of water, right? And the advantage of that setup is that you can lift and lower the pipe, and the water level will always close one end, right? So then you have an open end and a closed end. You can have a short pipe, you have a long pipe, okay? Right. And if you strike the tuning fork above it, then in certain places it'll resonate, right? So kind of like a blowing into a bottle, right? So it's not like this as you're changing the height of the pipe. It's like that. Now where it's resonating, that tells you something about there's being a standing wave setting up inside. Okay. Now we're talking about sound waves, so it is a longitudinal wave. Now longitudinal, that's the one that's really hard to draw because you have to sit here and like dot 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 dot. You're drawing all these air molecules. They're all bunched up in certain places. Where they're bunched up, that's like a high pressure point. Where they're spread out, that's like a low pressure point. Right? And since it's really hard to draw longitudinal waves, a lot of times you can actually whip off a transverse wave and say that represents a longitudinal wave. That's what this S-looking shape is right here, right? Where like crossed it over on itself, right? Although they're not really transverse, right? It's just easier to draw that way, right? And there's like a certain geometric pattern where it'll set up different standing waves. Okay? So like some musical instruments, say like a glass bottle might work on that type of principle. Okay? Now we're going to use this to actually calculate the speed of sound. So I'm like planting this idea today, and when we eventually get to this lab, right? Now how would that work? Well, you might remember from a few posters ago, you go back and dig this up, that speed is wavelength times frequency. So if you know the frequency, because it's stamped in the tuning fork, so many hertz, and you can figure out the wavelength, because you can raise and lower the pipe until it resonates a certain place, and pull out the meter stick and get some measurements for length, right? Then you can calculate the speed of the associated wave, so the speed of sound in that case, right? There's, of course, a textbook value for the speed of sound. It's about 330 meters per second at or 1 atmosphere and room temperature. Yeah, about 330, 340 meters per second. Yeah, so see how close you guys get to that eventually. Okay. All right. How about a pipe that's open at both ends? Ooh, this could be like a flute, a recorder, a lot of wind instruments, brass instruments, maybe some principle here, right? Where there's going to be low pressure points on the ends and a high pressure point in the middle, unless it says something like this. Maybe a couple of high pressure points, right? But there's like certain math that goes with that. Right? I have a video demo for this. What if you attach a string to an oscillator, right, and hang a weight over the other end, right? As you change this frequency, there's certain standing waves that you can set up at certain frequency values, right? Something like that. Okay. It's mathematical relationship there. How about any stringed instrument? I'm calling this a guitar string, but this could be a piano string. This could be a violin string, right? They usually set up standing transverse waves with half a wavelength. This right here, you're looking at half a wavelength. The other half a wavelength would be like off the page, the other half the story, okay? So this is half a wavelength. That's like this box down here. The wavelength would be twice the length of the string itself, right? Now, maybe you're trying to tune this guitar string, so you're like turning the peg to tune it, right? Okay, so you're trying to match a certain note frequency, right? Maybe you're trying to get like an A note, for example. Right? I want like 440 hertz, right? So that's that frequency, right? Right. So okay, so now we got a match here, right? And then there's some tension you need to achieve that. The string itself has some physical properties called that linear mass density, right? Mass per length, right? So there you go. There's the physics of tuning a string instrument. Be a lot you could do with that, right? How about musical notes? Different musical notes. Right. So there's actually two different type tuning systems on here. This is like Pythagorean tuning. If you want, say you want to set up a chord or a harmony that sounds really good, you'd actually want to use this note frequency ratios. Okay. Now, modern musical instruments actually don't exactly use this. They use something that approximates this. This actually is an exponential relationship here. Right. So, what is some note on a scale compared to some root note? Say, like if you have a nate note that's like 440 hertz, and you might have hit like the perfect fifth, right? Well, Pythagorean tuning says do like a 3-2 ratio, right? From that 440 hertz. Right? But if you use this equal temperament equation, you'll get something that's pretty close to that. Not exactly that, but pretty close. Right? Okay. Got a couple left here. So Doppler effect. Say you're standing out on the sidewalk, a car goes by, so it's like, you hear a pitch shift. If you're inside the car, you don't hear a pitch shift, but out on the sidewalk, you do. So what is the observed frequency compared to the source frequency? Right, got an equation for that. We'll run this. What if you're going faster than the speed of sound? Supersonic, faster than the speed of sound, right? You guys ever hear like Mach 2, Mach 3? That's like how many times you're going faster than the speed of sound. Right, so that's that ratio right there. Finally, how loud is a sound? You can measure that in decibels. It's a weird system too. We might talk about that in the future. All right, so here's the bell. Good pause point. Yeah, turn your lab to the great train, and you guys have a good day. I'll see you guys tomorrow for some demos.